All right, let's do now. What is the instantaneous rate of change at x equals 2 of the function f given by this equation? And let's find out what that will be. So I took the quotient rule. I didn't take the quotient rule, but I used the quotient rule. And now I'll be asking for the rate of change at 2. So let's plug in 2, see what we get. So that would be 4 minus 4 plus 2 all over 1, so which will be 2. Alrighty, so that will be the instantaneous rate of change when x equals 2. Next question. Jingle bells, jingle bells. Alright, the graph of the function f is shown in the figure above and has a vertical tangent at 0.20, which that means that if you were to create a tangent line, it would be very vertical. And a horizontal tangent at, so that's when the slope equals 0, for what values of x between this interval is f not differentiable? Well, clearly f is differentiable at these points, because at all of these points I can easily find a slope. The only ones that I'm not clear is, this one I know that this is not differentiable, because it's not continuous. And we know that if a function is not continuous, it's not differentiable. This one right here, I think that's when the vertical tangent is, right? So f has a vertical tangent, which means that it would not pass the vertical line test. If you have a vertical tangent right here, that means that there were at least 2 points on this line that are right above each other. That implies that one x gives you 2 y's. That makes it not a function. So the candidates that I would see it be would be, seems to me would be this one, with 0 and 2. And the reason is, if the reason was this one right here, right there, we had a, what's that discontinuity mean? Oh yeah, that's I think a step discontinuity. So it's not continuous, so it's not differentiable. And over here, this is not even a function at that point. So it's not differentiable. Alrighty, that's it. Before moving on, I do want to visit one concept real quick, in case because I'm pretty sure you understand why it's not differentiable right here. And that's because the last video heavily talked about it. But you're probably confused. Why does not passing the vertical line test imply that it's not differentiable? Well, think of it this way. If it's differentiable, we found the derivative. The derivative exists. And the derivative represents the slope. And the slope is rise over run. So if you have a vertical tangent, that means that your rise is infinitely bigger than the run, or the run is infinitely smaller than, or close to the number 0 than the rise. And you know, and especially if you're making the claim that a vertical tangent line exists, it means that there were 2 points that are right on top of each other. Meaning that if you had, let's say, 2 and then 1 for the y's, but they were on top of each other, meaning that they each had the same x. So let's say 3 minus 3, you ended up with a slope of 1 over 0. And that's undefined. So the derivative doesn't, you don't actually have a derivative. So since f prime, fc doesn't exist, because that's a fraction where the denominator is 0, does not exist, it's not differentiable at that number. Alrighty, so I hopefully that cleared it up. So this one is the one you knew for sure. I just tried to clear up if you were confused about why 2 would not be differentiable. Alright, today you're going to be learning about the derivatives of parametric functions. Let's say we have an x prime and a y prime, which I'll represent it this way, if you have the third variable being time. If you divide the dy dt over the dx dt, and then since the denominator can be brought forward but you have to flip it, then you can see that the dx will cancel, leaving you with dy dx. So you could make the statement that dy dx is the same thing as dy dt divided by dx dt. So here would be an example. We have an x function, we have a y function, each in terms of t. You can find the dy dt by taking the derivative the way you would normally do. So that would be 2, and that one would be 3. So you have your individual ones. But if you're trying to find out what dy dt is, dy dx, you divide the two, like we mentioned earlier. So it would be 2 divided by 3, and you would have your answer. That would be dy dx. Translate this equation into Cartesian equation. What is it? Write the equation of y in terms of x. Alrighty, that's just a substitution. You take 1. So let's say we take, let's see, yeah, that's what they did. They took this guy and then solved it for t and then plugged it into the other one. And that's pretty much how you convert it into Cartesian coordinates. So that will be your Cartesian coordinates. We actually did one like that in Albert I/O. If you remember, if you recall, a long time ago, we did one of those bad boys. And then you take the derivative of this, you would end up with the same thing. Example 2. Find dy dt, dx dt, and dy dx. Translate this equation into Cartesian equation. Oh, okay, there they are. I'm like, but what's x and what's y? So they're right here. By the way, you're probably thinking, why don't you just look on the slide before you start recording? I do not have the time for that. All right. So I have Mr. Waterman in my classroom.
Peanut gallery.
Peanut gallery. Alrighty. This is all happening in the video, by the way. I'm not going to go back to edit it out. All right. All right. dy dt is 1, dx dt is 2t. If you just take the derivatives, and then you do dy divided by dx to get dy dx. And translate this into Cartesian coordinates. So by the way, this can go either direction. So the way that they chose to do it is we took the x1, solved it for t, which would be square root of x, and then plugged it into here, which gives you this guy right here. So you end up getting x to the 1/2. You take the derivative of that, you get the same thing. You get the same thing. By the way, you're probably wondering, we did get the same thing because, boom, look at that. Well, if you were to solve for t, and if you took this equation, let me use green. If you took this equation and solved for t, then you would end up with square root of x. And if you plugged that in here, you would have gotten the exact same equation. Answer. By the way, one thing I want to highlight, you probably were wondering, if you take a square root on both sides, shouldn't you have gotten positive and negative square root of x? Well, if t represents time, then t cannot equal negative square root of x, because the square root of x is just going to be a positive number, since you can have a negative side of a square root, and t is time, and typically does not equal a negative value. Alright, let's see what we have here. A semi-cubical parabola problem. It's a big word. Parametric function has the equations, blah, blah, blah. Find dy dx when t equals 1. Okay, so you do your individual ones, so that would be 2t, and that would be 3t squared. Divide the 2. That's not correct. Oh, when you plug in t equals 1. Okay, yeah. Then that would be correct. So you would end up with this. I totally didn't see this side. Totally missed this. You would end up with this, but then when you're finding out what it is when t equals 1, you plug in 1 in here, you get derivative 2. Part B, find the tangent line to the point x and y when t equals 1. Find the tangent line to the point. Okay, so pretty much what is dy dx when t equals 1? So we already know that. We plugged in t equals 1, which is 2/3. So that's your slope. And we plug in t equals 1 into the x's and y's. So when you plug in 1 right here, you get x equals 1. When you plug in 1 over here, you get y equals 1. So into your equation, you plug in y equals 1, x equals 1, and then, by the way, this is called the point slope form, not the slope intercept form. And then you do some simple math, and you end up with your tangent line. Alrighty.
I do some math.
Yeah, math is important.
Math's hard.
Eliminate the parametric parameter t, find y in terms of x, find the result, state why this graph is called a semi-cubical parabola. By the way, in previous videos, I would like read a whole paragraph problem, and then I would totally missay a word and realize later, and then not change it, because they can read it, you know? They read way better than I do. Alrighty, x equals, oh, totally forgot what the problem is. Eliminate the parameter t, find y in terms of x, find the results. Okay, so use a substitution to do this. State why this graph is called a semi-cubical parabola. Anyways, so you want to find y's in terms of x, so that's when you do the substitution thing. You take one of them, solve it for t, plug it into here, and then you pretty much solve it out, boom, 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 and here will be your answer to that particular one. The reason why they say semi-cubical is, I'm guessing the fact that, assuming that t represents time, you always don't care about the plus or minus. But if that wasn't the case, over here you should have technically gotten t equals plus or minus square root of x, and if you plugged in the plus or minus in here, you should have gotten plus or minus, let me just write it real quick. You should have gotten I'll use a different color. You should have gotten a plus or minus right there, right? But because you're only including the positive one, it's half the cubical problem, because you're pretty much not caring about the negative ones. And just a little side note, if had this not been a 3, oh no, okay, you probably won't see it because I undid it, but I accidentally erased the 3. Had this not been a 3, had it been an even function, then it wouldn't have mattered, because if the square root of x would have been positive or negative, it would have canceled out the negative anyways. But given that that's not the case, we're gonna get rid of the plus or minus, since time cannot be negative. And that will be our thing. Find dy dx by direct differentiation of the equation in part D, and then this was crossed out, so we're not going to do it. We're not going to do whatever this said. So find dy dx by direct differentiation. Okay, if you just take the derivative, fine. That's easy. So, oh well, they did it right here. So let me just real quick. So you get 3/2 because you move that up front, and then 3/2 minus 1 is just 1/2. By the way, we're done. So that was the video. Talk to you guys later.